Ladies and gentlemen, welcome to the second chapter of our course on the formation of rocks, and now we are talking specifically about sedimentary rocks and sedimentary environments. In Marshak's textbook, that would be in chapter 7. Sedimentary environment means particles are deposited. These particles can be clay or sand grains or pebbles depending on the size of the particles. So clay would be very fine, sand are a little bit bigger, pebbles, cobbles obviously are larger. And typical sedimentary environments where such particles get transported or deposited or both. This would be rivers or streams, lakes, the sea obviously as the largest sink of sediments, or it could also be an aeolian environment. That means particles, sand grains driven by wind, which as you know in desert would then form dune belts. Once sediments are deposited as a loose and soft material, as you see it here, for instance, in these beach pictures that we see in these two photographs. They come to a rest, and if they are not eroded and not transported to another place during their geological history, they might become overlain by more and more sediment and eventually get solidified, and that would turn a sediment, which is a soft material, into a coherent rock, which, as we know, is a solid. This is what we are going to talk about transport processes, about deposition, about different kinds of sedimentary environments and how they can be distinguished on the basis of the sediments that form and subsequently of the rocks that form. Let's have a look at a few examples. Here, for instance, we see a steep cliff that is fairly close to the sea, and from that cliff, obviously, material will get eroded. It will simply physically be loosened up during weathering, and these rocks then will fall down onto this slope here, where fairly coarse-grained material that just comes from nearby comes to a rest for some time. And if there's water or melting snow in spring, or more material comes on top, it will get pushed down into the sea, where it eventually comes to rest and forms a sediment that might get solidified in the geological future. This is a way how this cliff eventually could be retreating further inland. Obviously, if water streams are here, that process is accelerated, and that also would have an influence on the material being washed into the sea here. Obviously, water will take all materials very quickly downstream if these particles are small enough to be moved by this kind of water, and this water here is fairly powerful. It flows very quickly down that fairly steep slope. Another example here of erosion and transport is this deeply incised river valley, as you can see in a desert environment. And we can see here on the sides of this valley there are exposed layers of different kinds of material. These here are sedimentary rocks, older sedimentary rocks that are already solidified, and where this river has cut into that landscape, we see that these rocks are eroded. We see this layer here continued across the valley once to this place here, and further on to the right hand side of this scenery, and all this material that once was present where now the river valley is got eroded and transported further downstream. We also can see that currently such erosion processes are happening, again in a similar form like here on the left image, that material is loosened up and falls down onto these slopes here and these materials we are calling talus. Talus is a term that you might want to look up in your textbook and in the glossary, where you find a definition of this term talus. The river itself obviously is flowing more or less fast, depending on season, depending on how much water is available. For instance, if upstream there are heavy rainfalls, you will get a flood, and this flood would be obviously more effective in transporting material downstream than a low water level. When the water is slowing down, when the stream velocity is slowing down, and you do not have much energy to actually transport larger particles. We will come back to that a bit later in this lecture. Another example here, this is what we would call a braided river system, large plains where small channels are either eroding or transporting material along. You see here these tiny little steps, and this is a fairly close up of a very large river plain. And here these little streams, they erode material in some places, and in other places material will come to a rest, and over time eventually material will be transported downstream, deposited, re-eroded, redeposited over a long time period. Eventually material will end up further downstream and perhaps in an environment where it gets buried under more and more sediments and eventually becomes a sedimentary rock. Here we see the situation in a more schematic rendering, in a schematic drawing, how weathering, erosion, transport and deposition are related, and this is the principal process that we will evaluate and investigate further in this section of the course. So what you see here is on the left hand side an area representing topographic high ground areas that are prone to weathering and eventually erosion. And weathering and erosion are two different things. They are very often confused or used as synonymous, but weathering is actually the physical interaction of water, of freezing water, of chemical processes with the rock that loosens up the rock or might dissolve the rock into water. And this process breaks down some minerals that loosens up a formerly very hard and solid rock. Once it is loosened up, the material can be transported more easily. So if a rock, for instance, experiences a lot of jointing and fragmentation, these smaller fragments can fall down a cliff and eventually be washed down a slope, ending up in river channels and being transported further down while being ground down to smaller and smaller particle size. This is a function of distance to the source. This area here we would refer to as a source of sediment, where erosion is an important factor, and the transport will eventually bring materials into different environments where they get modified or deposited in river systems or eventually in the sea. What we see here in these arrows, that is representing the dissolution of minerals. Some minerals can be dissolved in rainwater and in groundwater, and that particularly applies to salt minerals and to carbonate minerals. You all have heard of acid rain, of rain that has a certain pH value that is likely to interact with especially carbonate minerals. Carbonate can be dissolved very effectively, almost as effectively as salt, and the mineral that would mainly be dissolved is calcium carbonate. This will enrich groundwater in calcium ions and in carbonate anions, and these groundwaters then will carry that dissolved load. We come back to that term a little bit later. Also, surface water will be enriched in cations after interacting with rocks during the weathering stage. Weathering and erosion. We have used these two terms, and I want to emphasize again, weathering and erosion are different. Weathering is simply the physical or chemical disintegration of rocks, and contributing factors are freezing or melting of water that might expand and fracture rocks. Dissolution due to the low pH value of acidic rain, and abrasion by wind is another factor. All that can disintegrate rocks, and once they are disintegrated into smaller components, erosion can carry away the weathered material. So erosion is the transport of material. It carries away material from its original source on its pathway to its eventual sink, where it gets deposited and may get covered by other sediments. The sediment transport may be by ice or wind. Mostly that will happen through water, and the flow velocity and the water amount will control the nature of the sediment. For instance, the particle size. Grain size is controlled by flow velocity, and flow velocity usually correlates with a distance to the source of the sediment. In high mountain terrains where you find the sources, where you find the places where material gets weathered and eroded, you find more commonly coarser grained material. The further away you are from the source, the finer grained the material tends to be in river systems. Here we see an example, a field photograph of a sequence of sediments, and they seem to be not very strongly consolidated. So these are somewhere between a soft sediment and a consolidated rock. They form fairly steep faces here. That means they have some coherence. They are not entirely soft. But we also see here on the ground a lot of material that has fallen out of these layers. So what we see here are changes in material. We see sandy layers that are fairly fine-grained, and we see layers that contain a lot of pebbles. These would be obviously larger particles, and these larger particles tell us that the water that has transported them to this place must have been faster flowing than the water that has deposited the sand layers at another time. And these changes happened quite a few times. We see here a pebble-rich layer followed by a thin sand layer. Then we see here a layer with gravel, but no very large pebbles. Eventually here, larger pebbles followed by sand, pebbles, sand, pebbles, and then further alternations between these different materials. And these different materials tell us there was a variability in sediment supply and in flow energy that has deposited these sediments in the past. The nature of the sediment that we find in such outcrops, they represent a geological record and different environments where sediments can get deposited, such as rivers or the delta where rivers meet the sea, beach environments or deep sea environments. All of those environments have different characteristics. They are different in the terms of the water availability and the flow velocity of the water, and that is then represented in the particles that can get deposited, which in turn also allows us to conclude from the observation that we make in nature, in the geological record, we can conclude about the nature of the environment in which these sediment layers formed in the geological past. That is a very important approach. Geologists make observations of what happens in the present time, and compare these observations with what they find in the geological record. And that allows us to interpret the geological past. That is one of the very important principles by which geological research takes place. We observe in the current natural environment or in experimental work, and we try to compare the observations with what we observe in fossil systems, in geologically older systems. Here on this slide we see a representation how actually the sediment load is distributed in flowing water. And in order to describe that, we need a number of technical terms that distinguish between different parts of a water column in flowing environments. First, we need to talk about the dissolved sediment load, and we have mentioned that before. Rainwater and surface water can dissolve certain minerals. Salts and carbonates are particularly prone, but also other weathering processes can break down silicate minerals, for instance, and the dissolved material will be contained in the surface water or in the groundwater. And this dissolved material, that is referred to as the dissolved load in a water. Then there is the suspended load. The suspended load would be these very fine particles that remain in the water column and flow with the water without settling at the channel floor or at the bottom of a river. And then we have the bed load. The bed load are the larger particles. These are the particles that are too heavy to be suspended in the water. And they are sitting on the ground of the water channel where they might roll, pushed by the flowing water, might come to a rest and might get pushed a little bit further in the next flood, perhaps when the flow velocity is increasing. This is also something that can control local environments, because when you think there is a large pebble somewhere at the bottom of a river and the water flows over this pebble but can't move it, on the lee side, on the downstream side of this pebble, we will have an area where the water flow velocity is fairly slow, and that is where smaller particles can come to rest, although they normally would be driven further downward as part of the moving bed load. So here we need to think about different situations. Fast flowing water will be able to keep particles in suspension that will become part of the bed load when the flow velocity slows down, because slowly moving water cannot carry larger particles. So what is bed load and what is suspended load is not always the same. It depends on how fast the water flows. Then there is a process that is called saltation. And saltation is indicated here by these curving trajectories. These would be material pebbles that are transported by water but then bounce down and loosen up other particles that then also become part of the transported bed load. And these kinds of bouncing movements, that is also something that facilitates particles moving further downstream. Again, the intensity of the saltation depends on the flow energy, and flow energy in rivers, as you know, can change very quickly. For instance, if you have heavy rain further upstream, you will increase the flow velocity because you simply increase the volume of water that is in the river, and that will erode a lot of material that normally rests on the ground when the flow velocity is slower. So here we see again on this little inset the process of saltation. Clasts bounce along the bed and knock other clasts into flow. That tells it in very simple, quick words. Clasts is simply a technical term for a rock fragment that may form part of the bed load or part of the suspended load. In the suspended load, obviously, the clast size is much smaller than in the bed load. Here we see a few examples that illustrate these kinds of situations. Here we see a river that flows with a normal water load. It is fairly clear and transparent. That means it does not carry an awful lot of suspended load. We see the bed load through the water column here. These are the rocks and pebbles at the floor of the river. They probably move very slowly in such a situation. Here we see the same river after strong rains, when the water level rises and the flow velocity is much higher than here in this example. And here we see the water is murky. It has a lot of suspended load, and this is clay that is washed off the margins of the channels and is now suspended and is being transported downstream. At the same time, this high energy water, this fast flowing water, will also transport much more of the bed load than in this situation here. So periodically, the influence of rainfall, or perhaps snow melting in spring further upstream, if you are in environments where glaciers and snowfall occur, then you might have seasonally or periodically after rainfalls high water energy where normally the water energy is low. Here we see another example, an aerial photograph, where we can see that a fairly murky river with a lot of suspended load meets the shoreline and spills out all its water into the sea. And here from the color you can see how the fine-grained sediment is distributed in front of the shoreline here. That is an example from the Black Sea. The sea currents that are moving fairly slowly are carrying away the sediment, and you see here it is flowing into this direction. That would be the sea current that then takes over the distribution of the suspended load from further upstream. Here we see a kind of a braided river system with channels in a fairly fast flowing stream. These gravels form here these gravel bars that are flooded only when the water level is higher. But you can imagine in a high flood event, water would be everywhere, would be flowing much faster, and then the gravel that is resting here on these bars and also on the floor of the stream that is flooded at the present, these gravels would be transported further downstream. That is a part of sediment transport, depending on the available water amount and flow velocity. Two more examples here at the bottom. Again, a high mountain, fast-flowing river where the water is fairly clear because from the source area the fine-grained sediments have been removed. This fast-flowing water will be able to transport quite a few of these cobbles, and again, the more water is in the stream, the larger the cobbles are that can be transported, that can come into suspension or by saltation be moved further downstream. This example here is different. We see here a fairly slowly flowing river, and we see here muddy parts of formerly deposited sediments. These, what we call point bars, are currently not flooded and contain very fine-grained material. If there is a higher water level after rains, for instance, you can imagine they will get flooded and some of the fine particles will get suspended and be transported further downstream. So this is a kind of a periodical and cyclic process that transports successively sediments, particles downstream in waters again depending on water energy and flow velocity. This image here is a representation of these very different kind of environments from the sources of sediments in perhaps high mountainous terrains where erosion takes place, and eroded material becomes part of the bed load or suspended load of flowing water. In lakes, you might deposit some of it. Along fast-flowing rivers, you very effectively transport finer grain sizes and larger grain sizes, pebbles, cobbles, and with changes in topography to flatter and flatter terrain, the flow velocity will slow down. Rivers become different from narrow channels in high mountain terrains to braided river channels where still fairly fast-flowing water is available, to eventually slowly meandering rivers where we keep only the finest material in suspension, and these fine, muddy-looking waters might eventually meet the sea where they spread out and distribute the sediment load, eventually coming to rest in a marine environment. There is no good chance to produce coarse-grained sediments in such a delta or marine environment simply because these areas are often too far away from the sediment source. We are going to talk about some of these environments in more detail in the next lecture. Before we come to that, let's have a look at the fate of particles during transport.